So today I would like to talk about unilateral Laplace transform. Okay, so we know that the equation for Laplace transform is L of x of t is equal to integral minus infinity to plus infinity x of t into e raised to minus st dt. This is the equation for Laplace transform. Okay, unilateral Laplace transform is basically used for those signals that are causal in nature. That is, if this x of t is causal, then in that case, then I don't need to apply my limits from minus infinity to plus infinity. My limits will then become 0 to infinity. That is the meaning of unilateral. Uni means one-sided Laplace transform. Okay, the reason is we all know what is a causal signal. A causal signal is a signal that depends only on the present and the past values, right? So if you take a graph, this x of t, if x of t is a causal signal, then all the values will be present only in the positive side of the graph, positive side of the y-axis. So this is what you call as the causal signal. That means the value of x of t is 0 when t is negative, and x of t only exists when t is from 0 to plus infinity. So in that case, those kind of signals we are calling it as a causal signal. And since, like we said before, since the value of x of t is 0 from minus infinity to 0, then the Laplace transform of that signal also is 0. Therefore, the Laplace transform, the unilateral Laplace transform equation will then become integral 0 to infinity x of t into e raised to minus st dt. This is called as the unilateral Laplace transform equation. Okay, it's applied solely only for the causal signals. Okay, so how do you define a causal signal is just see to it that those signals are only present for the positive values of time t. That is, the signal x of t must depend only on the past and the present values. Okay, such signals are called as causal signals, and the Laplace transform applied on the causal signal is called as the unilateral Laplace transform. And another way of easily identifying the Laplace transform is, if you see any question, any signal, for example, if I just simply write a signal like this, e raised to minus phi t, okay, this is just a signal, okay, and this is now, it's not anti-causal or can be causal. It depends on the graph of this signal. But if I multiply the signal with u of t, then I am basically making the signal into a unilateral signal. I am basically making this into a causal signal. So in that case, I can use a unilateral Laplace transform. As you all know, the value of u of t is 1 from 0 to infinity. That means from minus infinity to 0, u of t becomes 0. So it's natural that e raised to minus phi t u of t is a causal signal. See, so in that case only we use this unilateral Laplace transform. One of the main advantage of using a unilateral Laplace transform is that if we apply Laplace transform to any other signal, then we can simply learn the property of that signal. We can simply learn that equation for that signal, and then we can substitute that equation for further coming problems. That is one of the advantage of unilateral Laplace transform. That means any derivation that I have committed over here, you can simply apply that derivation to other problems also. So that's what makes the problems more easier. In the previous cases and all, you have to substitute the value of the Laplace transform as integral x of t e raised to minus st dt. But here, all you need to do is just simply apply the property of that particular signal. So let's start with the symbol. Suppose if I want to find the unilateral Laplace transform of a unit impulse signal del of t. I want to find the unilateral Laplace transform of del of t. So how do I find it? This is equal to integral 0 to infinity del of t into e raised to minus st dt. This is the equation. We know the property of del of t. Del of t is a unit impulse signal in which the value of del of t is equal to 1 exactly when t is equal to 0. That's how we substitute. The integral of this del of t is equal to 1 when t is equal to 0. So that means in this equation, if I substitute t is equal to 0, then I will get over here as 1, and this will become e raised to 0. This will become 1. Therefore, I can say that the Laplace transform of del of t is equal to 1. This can be used as your first equation. Your first rule, a very simple rule. So now when you see this del of t anywhere, you don't have to apply this same equation again. Just simply apply the direct answer over here. That will make your problem so easy. Next thing is, if you want to find the Laplace transform of course all of you know this, the Laplace transform of a unit step signal. So if I apply the unilateral Laplace transform to u of t, I will get 0 to infinity u of t into e raised to minus st dt. The value of u of t from 0 to infinity is 1. So this will become into integral 0 to infinity e raised to minus st dt. This will in turn will become 1 by s into e raised to minus st from 0 to infinity. This will become 1 by s into e raised to minus infinity minus e raised to 0. So this will become 1 by s. So hence we have learned the second rule, that is the Laplace transform, unilateral Laplace transform of u of t is equal to 1 by s. Learn these equations. It will help you for your future problems. The next equation you're going to apply is, you can find the Laplace transform of cos ohm 0 t. So let me find the value. Unilateral Laplace transform of cos ohm 0 t. Okay, this is equal to integral 0 to infinity cos ohm 0 t into e raised to minus st dt. Okay, I can substitute cos ohm 0 t as e raised to j ohm 0 t plus e raised to minus j ohm 0 t by 2. I'm going to substitute that equation over here. That means this will become integral 0 to infinity e raised to j ohm 0 t plus e raised to minus j ohm 0 t by 2 into e raised to minus st dt. I can take this denominator 2 common, so this will become 1 by 2 into integral 0 to infinity. Now I can multiply e raised to minus t inside the bracket. This will become e raised to j ohm 0 t into e raised to minus st plus e raised to minus j ohm 0 t into e raised to minus st dt. Okay, now I can combine these two exponential functions together. 1 by 2 integral 0 to infinity e raised to minus of, I can write here s minus j ohm 0 t. Yes, here also I can write it as plus e raised to minus of s plus j ohm 0 t dt. Okay, so now I am going to integrate both of them. 0 to infinity e raised to minus of s minus j ohm 0 into t dt plus integral 0 to infinity e raised to minus of s plus j ohm 0 t dt and now on applying integration I will get 1 by 2 into, this will become minus 1 by s minus j ohm 0 into e raised to minus s minus j ohm 0 t from 0 to infinity plus minus 1 by s plus j ohm 0 into e raised to minus of s plus j ohm 0 t from 0 to infinity. This will also become, this will in turn it will become 1 by 2 into, if I substitute the values over here I will get 1 by s minus j ohm 0 plus, this will also become 1 by s plus j ohm 0. Yes, because if I substitute infinity away it becomes e raised to minus infinity, then after e raised to minus infinity minus e raised to 0, e raised to minus infinity is 0, so 0 minus 1 minus 1 minus 1 into minus 1 plus 1, so it becomes plus 1. Similarly over here also, if I substitute infinity over here it becomes e raised to minus infinity, if I substitute 0 over here it becomes e raised to 0, so e raised to minus infinity minus e raised to 0, so it means e raised to 0 minus 1 into minus 1 is positive, so I get this value. Okay, this is also equal to 1 by 2 into, I'm going to now do cross multiply, so this will become into s plus j ohm 0 plus s minus j ohm 0 by s minus j ohm 0 into s plus j ohm 0. Okay, so you will get over here as 2s by 2 into, if I cross multiply these two I will get s square plus ohm 0 square. It's a complex number, multiplication of a complex number with its conjugate, you will get a square plus b square. So now if I cancel 2, this is my final answer, s by s square plus ohm 0 square. So hence I found my second property, my third property, that is the Laplace transform of cos ohm 0 t is equal to s by s square plus ohm 0 square. You can now, you need not apply the Laplace transform of cos ohm 0 t in the coming problems. All you need to do is simply apply this equation. Okay. Next, similarly, I can now find the Laplace transform of sin ohm 0 t. I can now find the value of sin ohm 0 t. Okay, and here also the procedure of this is exactly the same as before, no difference, except that we know that this the equation for sin ohm 0 t. The equation for sin ohm 0 t is e raised to j ohm 0 t minus e raised to minus j ohm 0 t by 2j. All you need to do is just substitute this equation over here and continue as and proceed as before, and finally you will get the equation as the Laplace transform of sin ohm 0 t is equal to ohm 0 by s square plus ohm 0 square. So that is your next equation. See, so this is the advantage of unilateral Laplace transform. Once you derive these kinds of unique properties for these kinds of standard signals that you need not derive them in the future coming problems. You can simply by heart these properties, just understand and by heart these equations. Then in the coming problems it will be very easy. All you have to do is just simply substitute these given equations in the coming problems. That is the advantage of unilateral Laplace transform. Okay, so we will move on to the next problem. Okay.